So dear students, here we are going to see one of the experiment called as colorimetric method. So our experiment name is colorimetric method. In this experiment, if we talk about the aim of the experiment is to determine the maximum wavelength of absorption of copper sulphate solution. So right now we are having copper sulphate solution. Verify Beer's law and find unknown concentration of given copper sulphate sample. So to begin with, we have apparatus, colorimeter, beaker and cuvette, and we have chemicals, that is copper sulphate solution with various concentration. So let us understand what theory behind it. So like we are verifying Beer's law, where I can say the Beer's law is A equal to epsilon C L. So what does it mean by A, epsilon and C and L? So A is nothing but absorbance, epsilon is molar extinction coefficient, C is concentration of the solution and L is the thickness of the solution. So if we understand absorbance means it is likely to be absorb some radiations. So as we know that water sample, tea or any colored material that absorbs radiation. So the same phenomenon here is going on with respect to solution. So the solution like copper sulphate solution absorbs radiation. Now how much radiation is it absorbed? That we are going to see depends upon the concentration. So according to the equation, that is A equal to epsilon CL, you can say absorbance is directly proportional to the concentration if thickness of the solution is constant. So by keeping thickness of the solution constant, we are going to find out the absorbance of different concentration of the solution, and then we can verify the Beer's law. So we have a standard procedure for determination of first lambda max of the copper sulphate solution. Now to find out the lambda max value, that is maximum wavelength of absorption, we have to take a solution which is of higher concentration. So while performing the experiment, we will take the higher concentration sample and then we will perform this part A. So in this part A, we have to take a colorimeter. In that colorimeter, we are having a filter, wavelength filter, and that wavelength filter, whenever we select it, let us say if we are selecting 400 nanometer wavelength filter, in that case it needs to be standardized. So how it is standardized and how it occurs, let us understand while practical also, as well as I am explaining here. So first we need to see the colorimeter where we are having absorbance and transmittance, which is shown in the colorimeter, and then we have to keep the water sample in the sample holder where it should show the 0 absorbance and 100% transmittance for water sample. As we know that water sample does not absorb radiation, it only transmits the radiation, and absorbance value in that case will be 0. So before selecting each wavelength, before taking a reading of highest concentration sample for each wavelength, we have to standardize colorimeter for each wavelength filter. So by selecting different wavelength filter, we will note down the concentration of highest concentration sample. So this is what the part A, where we will determine the absorbance at different wavelength. So in the part B, what we are going to do, we are going to verify Beer's law and determine the unknown concentration of solution. So for that, as we have seen in the part A, whatsoever the wavelength which is showing the maximum absorption, that particular wavelength will be called as maximum wavelength of absorption, and by using by selecting that particular wavelength, we have to perform the next part, that is part B, that is called as verification of Beer's law. Wherein what we will do, we will take various sample of copper sulphate solution, and then we will determine how much absorbance it has, and accordingly we will come to know how exactly the trend is going on with respect to the concentration. So whatsoever the trend, if the trend is linear, we can say the Beer's law is verified. Okay. So in this way we can verify the Beer's law, where we will find out the straight line passing through origin for the graph which we will plot later on. So in this way we can perform the experiment. So here remember, we have to plot two graphs. One is wavelength versus absorbance, where we will be getting some maxima, and that maxima shows the maximum wavelength of absorption. In the second graph we will get a straight line where it shows that absorbance depends upon the concentration. So as concentration increases, absorbance should increase. So in this way we can perform the experiment. Now here we are going to begin with the experimental part, where you can see this is our colorimeter, and these are the different solutions which are having various concentrations. So you can see we have a solution of 0.5, 1, 1.5, 2.0, 2.5 and unknown concentration solution. So you can see this apparatus, that is instrument called as colorimeter, where we are having the various wavelength filter. So in this case you can see this is one of the wavelength filter in our colorimeter. So this particular wavelength filter can be rotated. So this is a specially wavelength filter, or we can say wavelength wheel, which can fix the wavelength of radiation. So to understand what we are going to do, we are going to fill this cuvette by using water. So I am taking a water sample. So you can see this is a water sample, where I can tell you one thing: this water is nothing but transparent in nature. So therefore you can observe one thing over here. We have two things in this case. One is absorbance and one is transmittance. And as we know that the water through which all lights transmit easily, therefore I can say light is transmitted thoroughly through the water, so water will be having 100% transmittance, whereas it will not absorb any radiation. So you can say it will not absorb any radiation, so zero absorbance. So let's keep it in the sample holder. So when we keep it in a sample holder, you can see the absorbance is around 0.01 and transmittance is around 96. So by using this adjust button, we can adjust the transmittance. So we can absorb, we can see the transmittance 100% and absorbance 0. So at each wavelength we have to adjust, or we have to standardize this particular colorimeter. So whenever we are rotating this, we have to standardize. So in this way we can standardize. So let us see the first reading for highest concentration sample, which is 2.5% sample. So here we are going to take a 2.5% concentration sample. So you can see here we are having the various sample, out of which I am selecting 2.5% sample, which is the highest concentration sample, because this particular sample will absorb maximum radiation. As we know that if the concentration is more, of course the electromagnetic radiation will be absorbed more. So by using the same concept, the same thing which we are going to prove, of course, we will first determine the lambda max of this highest concentration sample. So for that I already standardized this colorimeter for this 400 nanometer sample or 400 nanometer filter, where I will get the absorbance like 0.21. So in this way we can take the first reading at 400 nanometer. Now second reading we have to take by rotating this wheel to the 420 nanometer, where again I have to standardize it by using water sample. So you can observe here for the water sample it is showing the absorbance 0.21 and transmittance it is not showing properly. So we have to adjust it by using adjust button. Even though there are certain issues or errors takes place while performing this experiment. So like you can observe over here we are likely to be getting an error. So that error may occurs, and we can remove it easily. So therefore we can again standardize it at 420 nanometer wavelength filter. So accordingly it is standardized. Again what I will do, I will keep this highest concentration sample in sample holder to note down the next reading. So you can see there is a fluctuation in the absorbance. So at first we got the absorbance of 0.21, now it is 0.04. Now again we will rotate the wheel to 470 nanometer, where I can say I can again standardize it. So here you can see the absorbance, it shows not equal to 0 and transmittance 65. So again I have to adjust this transmittance. So transmittance is 100 and absorbance is 0. So again I will keep the highest concentration sample where I will get the absorbance. So absorbance is 0.9. So again I will rotate the wheel to 500 nanometer. Again I will adjust this transmittance to 100. Right? So again I will note down the reading. So it is 0.05. Again I will rotate the wheel, keep the water sample and adjust this transmittance. Right? So you can see here I am taking the absorbance 0.09. Then again I will rotate the wheel, keep the water sample, and then again adjusting the transmittance to 100. Here we are getting 0.23. So again I will remove this, I will adjust it to 660, and then I will keep the water sample and I will adjust the transmittance to 100. Right? So I will again note down the absorbance of this sample. So it is 0.35.
I will again rotate the wheel. Here I will keep the water sample and I will adjust the transmittance to 100. I will note down the reading for this highest concentration sample. So it is 0.84. Thus, you can say, as we were talking about the various reading you can see this is the reading highest and it shows highest absorption at 700 nanometer. So therefore, you can call this 700 nanometer as a maximum wavelength of absorption. Now, in part A, we learned that this 700 nanometer is the maximum wavelength of absorption. So by using this, we will verify Beer's law. Now, to verify Beer's law, we need these various samples. One thing you can note, in the part A, we have kept this particular highest concentration sample constant and we have constantly changed this wavelength filter. Here in this part, in the part B, we are going to fix this wavelength filter and we are going to change this various sample. So, now I am already having the reading for this highest concentration sample, that is 0.83. So, what I will do, I will change the sample. So, this is the second sample whose absorbance is 0.70. Make sure that whenever we are changing the concentration, whenever we are changing the solution, we have to clean this particular cuvette and then we have to fill the solution. So now we are getting the reading around 0.59. So it is a 1.5% sample which I have taken. Now I will take the solution where we are having the concentration 1.0. So you can see the reading where we are getting around 0.38 for 1.0. So here we are getting a decrease in the absorbance value. And finally, we are going to take the reading for 0.5% sample. So for the 0.5% sample, I will be getting some reading around 0.18. So in this way you can understand and accordingly you can say there is a decrease in the concentration and therefore there is a decrease in the absorbance value. So in this way we can say as absorbance is observed to be decreased due to the concentration decrease, right? So we can say as concentration decreases, absorbance decreases. Or in other word we can say as concentration increases, absorbance increases. So it verifies Beer's law. At this last we can say we are having one of the unknown solution whose concentration is to be determined. So for which I will take the unknown concentration solution whose concentration is not known. and when I keep it in a sample holder, it shows around 0.56. So by using graph, we can determine the concentration of unknown solution. Thank you.
So like we have performed the experiment where we got the observations. So like these are the observations which we have, and now we are going to plot the graph where we will plot a graph between the wavelength and absorbance. So if you see, we are having a wavelength versus absorbance graph where we are going to put the values. So accordingly, we will be getting this particular graph where you can see we are having 0.84 absorbance at 700 nanometer. So therefore, I can say this particular value or this particular wavelength is called as lambda max. So therefore, lambda max equal to 700 nanometer. In this way, we can select this lambda max for the next part where we are going to verify Beer's law. So for verification Beer's law, we are getting this particular readings. So by using this reading, we can say, like you can observe for 0.5 we are getting 0.18, for 1 0.38, 1.5, 0.59. So it is a linear value which we are getting. So from which I can conclude that Beer's law is verified, but this needs a proof of graph. So let us draw a graph. So if you plot a graph between concentration and absorbance, the plot is linear in nature. Though you may have some error or may have some less accuracy, that's why you may not be getting a straight line exactly. But if I draw a straight line, I can draw it. So if you see the straight line which is passing through origin, and therefore you can say as concentration increases, absorbance also increases. So therefore we can say from graph Beer's law is verified, and we can say if we want to know the unknown concentration of the solution, if we see we are having 0.56 as absorbance of unknown concentration solution, we can plot a line and we can come to know that unknown concentration of the solution is 1.25 percentage. So in this way we can perform the practical where we are getting a result, that is lambda max equal to 700 nanometer and concentration of the given unknown sample is 1.25%. So in this way we can verify Beer's law, we can determine the maximum wavelength of absorption, and we can determine the concentration of the given sample. So thank you.